Okay, all right. Now we will first chapter 1. Introduction to vectors. Okay. Now we give a definition. What is a vector? Definition. Okay, a vector is an object that puts that has both a magnitude and a direction. Magnitude and a direction. Okay, there are many examples. So how do we represent a vector? So we use an arrow. Okay, we can. So for instance, we plot this thing, and then we have tail. We have a head. Okay, we have head and tail. So we can represent this vector geometrically by a line segment, by an arrow. Okay, we can represent a vector by a directed line segment. Okay, line segment. The length of this line segment is the magnitude of the vector, the length. And the direction of this vector is just from its tail to its head. Okay, the length of the line segment. The length gives us the magnitude. Is the magnitude of the vector. And the direction. The direction is given by is from its tail to its head. Okay. Examples. If you study physics, you will have many examples. For instance, force. Okay. To give a force, you need to tell how big the force is. Okay, and also you need to tell the direction of the force. Okay, the direction of the force. For instance, velocity. Okay, you need to tell the magnitude of the velocity. The magnitude gives us the speed of speed of an object, but velocity also have direction. Okay, direction. For instance, acceleration. Acceleration A. Okay, displacement. S. Okay, etc. etc. Okay. Now we can also, another form of vectors is we can use coordinate to represent vectors. This is the idea of analytic geometry. We introduce coordinate to represent some points, lines, planes. Okay, the idea of analytic geometry. So we can also represent other representations of vectors. Of a vector by coordinate. Okay. So for instance, if we put into coordinate, we have xy coordinate. Now for instance, it's 1, 2, 3. And vertical, we have 1 here. Now suppose we have 2 points. Suppose we have A, 1, 1. Suppose we choose B to be, for instance, we choose it to be 3, 2. So we have B. So this is A, this is B. Then the vector AB. So directed line segment. Okay. So we can use AB. Okay. AB. Vector AB. Vector AB. So in coordinate form, the vector is to obtain the coordinate of a vector, we use head minus tail. Okay, head minus tail. So for instance, the head coordinate is B 3, 2. Okay, so 3, 2 minus 1, 1. So then we get 3 minus 1, 2 minus 1. Then we get the vector is 2, 1. Okay, we get the vector form, coordinate form of this vector. Okay, very easy. Now, how do we get the line segment is the magnitude of this vector? The magnitude of this vector. Well, that's very easy. This is very easy. We can apply Pythagorean theorem to find the magnitude. Okay, you see by Pythagorean theorem, distance. Or you use distance formula between 2 points. Okay, so the line segment will be AB. The magnitude. Or you call it as a norm. Okay, norm of AB. So we call it a norm of AB. So we call it a norm of AB. Or magnitude, or length of this vector. They are the same thing. Length of AB. Length of a vector AB. Norm of a vector AB. Or magnitude. They are the same thing. Magnitude of AB. They are the same thing. Okay, they are the same. So we can use distance formula or Pythagorean theorem. 2 squared plus 1 squared. Okay, by Pythagorean. So this is very easy. So we get a square root of 5. So what we used is we used the Pythagorean theorem. By Pythagorean theorem. Okay. So this is the vector in the 2-dimensional space, xy plane. Okay. Now, of course, we can have higher dimensional. We can study vector in higher dimensional space, like XYZ, 3-dimensional space. For instance, example. Now, if we are in 3-dimensional space, then suppose we have XYZ. Okay. When you plot 3-dimensional coordinate, okay, coordinate frame, what we usually choose the direction of the Z direction is, we use a right hand coordinate. So here the direction of Z, for this example, in this example, you may choose Z upward, you may choose Z downward. Okay, they are different coordinates. So the standard thing that we use is right hand coordinate. It's by convention. It's not wrong if you use the left hand coordinate, but it's unconventional. Now suppose we have 2 points. A in this with, for instance, xy, yy, zy, and B with x2, y2, z2. Then the vector AB is head minus tail. Okay, suppose we have A, we have B. Okay. Okay, so this is the x, xy, yy. This is zy. This is the A. Now suppose we have B, another coordinate B. Suppose we have this projection. Okay, let's see. This B is here. B. Then the direction from A to B. Okay, so just in short, the coordinate of a vector is head minus tail. Okay, head minus tail. Very easy. Okay, so for instance, if we have this, if we have a point P, example, X, Y, Z. So suppose we have a point P. O is 0, 0. O is 0, 0, 0, origin. Now suppose we have a point P, Y, Y, Y. Now its X, Y, Z coordinate is Y, Y, and the Z is direction is also Y. Then we have OP is head minus tail, Y minus 0 is just 1, Y minus 0, Y minus 0. So it's Y, Y, Y. So you can find OP, the length of this vector OP.
Can I know?
Here, question?
Yeah, I have a question. So like in this, like the third graph you draw, like where is the P point? Is like the
P point, yes, P is this one.
Okay.
Yeah. Then we have OP. Okay, OP. Okay, OP. Now you see this OP is nothing else, is the diagonal of a cube. You see, if we plot this manner, you see this will be a diagonal of a cube. Yeah? OP is the diagonal of the cube. So OP is one of the diagonal, is a diagonal line segment of a unit cube. Okay, unit cube. So the OP is sum of squares and then take square root. So this will be square root 3. So you see, use vectors. It's really convenient to do length. Okay, to do geometry. Okay. Actually, this is actually how vectors is designed. It was invented. It is a tool, a really useful tool to do geometry. Okay, to do geometry. Now we define vectors. And then we want to study how they behaves with respect to the Euro operations. Okay, can we define, the Euro operations? Addition, subtraction, multiplication, division. Okay. So now we define operations on vectors. Okay. Operations on vectors. Operations on vectors. Now, how do we define sum of two vectors? So for instance, if we have two vectors, A, and we have another vector B, how do we add them? So for instance, let's plot two vectors. Okay, suppose this is A, Okay, this vector A. Now suppose we have another vector B. This is vector B. Suppose it's A, OA, OB. This is vector B. Now the addition for vectors is we have the parallelogram law. Okay, we have the parallelogram law. Parallelogram law. Okay, we plot a parallelogram that are parallel to the two sides. Okay, plot a parallelogram. It's not a parallel yet. Let me do here. Okay, so this is the parallelogram. So we get a parallelogram. Okay, now this point, let's see it is to be C. So we determine a parallelogram. Then OC will be defined as the sum of the vector A and vector B. OC, okay. So this is A plus B. So the diagonal is called the sum of this vector, okay, A and B. This is defined geometrically. Okay, so to add two vectors, if they have the same tail, if that we put their tail all together, then we use the parallelogram law. Okay, we use the parallelogram law. Now, how do we subtract vectors? Well, we define. Now, if we have two vectors A and B, how do we define A minus B? Well, we define A minus B to be A plus minus B. Minus B. Minus B is the negative vector. Negative. So we flip the direction. Suppose we have this. Suppose we have vector B. Okay. If this is vector B. Now how do we define negative B? Well, we flip the direction. We switch head with tail. Then we get negative B. Any questions? Okay. So once we so for instance, this is A. Now this is the B. How do we find A minus B? Well, A minus B, we need A plus negative B. A plus negative B. Then we get we flip the direction of a B. So this we get negative B. This we get A. Okay. So if two vectors connected head tail, then we can connect in this manner. So this will be, let me use a different color. Okay, this will be A plus B, A minus B, sorry. A plus negative B. This is A plus negative B. Okay, so this, oh, sorry. Let me write here. This is the A plus negative B. A plus negative B. Or negative B plus A. So if two vectors together, we can in this manner. Okay. So now this also agree with the addition law, the parallelogram law. Okay, the parallelogram law. So for instance, this does not contradict the parallelogram law, of course. So suppose this is A, this is B. Okay. For instance, if we translate B, so this is this what I just plot is again B. Okay, it's parallel with B, so it is in the same direction as the vector B. Okay, so suppose it's A, B, OAB, C. Now you see AC is in the same direction of AB, OB. Okay. And they have the same magnitude. AC and OB are in the same direction, and they are the same, they have the same magnitude. So this means they are the same vector, okay? They are the same vector. So by what we just did, if we add two vectors, we can put head and tail together. So head, tail together, so you see this is again A plus B. Okay, you can add vectors by put head and tail together, or you can use the parallelogram law. Okay, you can also use the parallelogram law. They are equivalent. Okay. Okay. Now we can also multiply a scalar. Multiply a vector by a scalar. So this is called scalar multiplication. Scalar multiplication. Scalar multiplication. Now, if we have a vector A, we multiply it by a scalar. Multiply by lambda. And then output is lambda A. Lambda A. Now here lambda is a real number. Lambda is a real number. Now this is called scalar multiplication. Now we define scalar multiplication by the following. Okay. So lambda A is a vector. We define it to be this. If lambda is positive, then lambda A has the same direction. As a vector A, and it has its length, its magnitude, and it has length lambda A norm. Okay, so we just rescale this vector by a factor lambda. Okay, for instance, suppose this is A. This is A. Now, how do we get twice of A? Twice A. This is A. We add another copy of A. So this is actually twice of A. So we get 2A. In the same direction as A, but as a magnitude multiplied by the vector 2, by factor 2. Okay. Now, of course, this is we stretches the vector by a factor 2. If lambda is less than, so lambda is from 0 to 1, we just compress. Okay, compress. So for instance, if this is A, so vector A, how do we get half A? Half A. We just make it to be 1/2 distance. Okay, the length to be 1/2. So this is 1/2 of A. Okay, same direction as A. Now, if we get a negative, if we multiply by negative number, then we just flip the direction. Okay, so we just rescale the length, then flip by a direction, flip the direction. Okay, so for instance, if this is A, suppose this is A, now how do we get a negative to A? Negative to A is, we flip the direction. Flip the direction. Maybe I'll just make it shorter. This is A. Now negative A, so this we get negative A, we flip the direction. So this we get another copy of negative A. So this will get, this will be negative 2A. Okay, negative 2A. Flip the direction and rescale the length if we multiply by negative number. Okay. Okay. This is very easy, very easy. Now, what does these operations do? How do we do these operations on if we use coordinate? Okay, how do we use coordinate? Okay, If we, so this is geometrically, we just rescale. Now, how do we do algebraically? Now, algebraically, we just multiply algebraically. Algebraically, if we multiply, if A coordinate A1, A2, and B2 or B is B1, B2. So let me add them. Add two vectors. We just simply add the coordinate. Okay, we simply add the coordinate. And then if we multiply by a lambda, scalar multiplication, then we just multiply component-wise, multiply by component-wise, component-wise multiplication. Okay, so the picture looks like this. Suppose it's A, this vector A. Now we can decompose it to be horizontal and vertical. Suppose this is B. Okay, this is B. So this is part. This part is A1. Okay. Now this part is B1. This vertical part is A2, and this vertical part is B2. So if we add them together, A1, A plus B, the vector A plus B. If we add the vector A and B, then we get, you see, horizontal part will be the vector, the horizontal component of this vector will be, this will be A1 plus B1. And then the vertical part will be A2 plus B2. Okay, so we got this is A plus B. So this explains how we add vectors by coordinate, okay, using coordinate. So in short, to add two vectors, we simply add their coordinate, okay, add the corresponding coordinate. And then to multiply a vector by a scalar, we multiply its component, its coordinate by this scalar lambda, okay? Okay, let's do some examples about the very easy example. Very easy example. The operations on vectors. So suppose we have A, vector A, which is a 4, 0, 3. B as the vector -2, 1, 5. That's what we find norm of A. Norm of B. A plus B. A minus B. 2A plus 5B. Okay. Now A, the norm of A, we use Pythagorean theorem. Norm of A is, okay, sum of the squares and then sum of the squares of the component. And then take a square root. So this we get 16 plus 9, which is 25, which is 3, 4, 5 triangle. So we get a square root of 25, which is we get a 5. So norm of A is 5. Norm of B, similarly, we add the squares, and then take a square root. If you compute this will be 30, which is already easy. Okay, square root 30. Now, what is A plus B? Vector A plus B, we add them component-wise. component-wise addition. So this we get a 4 minus 2 x coordinate, the first coordinate, second coordinate 0 plus 1, and 3 plus 5. And then we get this is 2 y 8. Very easy, very easy. A minus b, then we subtract the component. Very easy, super easy. So this is just component wise subtraction. So we get a 4 subtract negative 2, so plus 2. 4 subtract negative 2, 0 subtract 1, 3 subtract 5. So this is 6 negative 1 negative 2. Okay, then 2a plus 5b. Very easy. So 2a, we multiply component wise plus 5b. Okay, we do multiplication first, okay, and then multiply component wise. So 2 times 4, so we get 8. 2 times 0, we get a 0. 2 times 3, we get a 6. Now 5 times negative 2, we get a negative 10. 5 times 1, we get a 5. 5 times 5, we get a 25. And then add the components. So 8 plus negative 10, so we get a negative 2. 0 plus 5, we get a 5. 6 plus 25, we get 31. Then we're done. Okay, then we're done. Okay. A special kind of a vector is actually a vector that has unit length. These vectors are called unit vectors. Unit vectors. Definition: a vector V is called a unit vector. A unit vector. If its length, its magnitude of this vector V is 1, i.e., it has unit length. Okay, example, if we have a unit circle, then we have a unit radius. Okay, now let me plot a unit circle. Okay, let's plot a unit circle. Okay, so we have a unit circle. We have X direction. We have Y direction. And we have this center O. Suppose we have point P. So this is the P. P is a point on the circle. So the unit circle. Which means the radius is 1. So we get OP. The magnitude is 1. Now, if you write down the vector OP, how do we write down vector OP? Suppose we have an angle theta. So suppose this angle is theta. How do you find the coordinate of P? What is the XY coordinate of P? What is XY coordinate of P? XY coordinate of P, we can find by geometry, okay? X coordinate is cosine theta, okay? If you solve geometry, solve a triangle. This you get sine theta, okay? So if you solve the right triangle, you see OP is 1. Okay, OP is 1. OP is 1. And this is theta. So this is you get this is cosine theta. And this you get sine theta. Okay, so we get the coordinate of P. So we get OP. O is center. O is the origin. O 0 0. XY is 0. So OP is cosine theta minus 0. Just cosine theta. Sine theta minus 0, which is just sine theta. Now OP, of course, there's no surprise. OP magnitude of OP by Pythagorean theorem. Then we get cosine squared plus sine squared, which is 1. Square root of 1, which is 1. So OP is an example of a unit vector. Okay, OP is a unit vector. Okay. Now, given a vector, we can produce a unit vector along this the given direction by dividing its norm. Okay. Given a vector A, we may construct a unit vector in the same direction as A. So we just the same vector A, but we divide by its norm. Okay, divide by its norm. Okay, then we divide its norm, then we get a vector. So this, which is a unit vector, then in the direction of A. Okay. For example, this process is called normalization. We normalize it. So for instance, A is 3, 4. Now the norm of A. So 3, 4 is this 1, 2, 3, 1, 2, 3, 4. Okay, so 3, 4 is here. O, let's see, this is the OA X. This is 3, and this is the 4. So the magnitude is 3, 4, 5 triangle. Okay, so you get the norm of A is 3 squared plus 4 squared, take a square root. We get a square root of 25, which is 5. So its norm is 5. So we can normalize this. So we get a normal vector. So we get a unit vector. Okay, you can check. This is a unit vector, which is a unit vector. So we can normalize a vector by dividing its norm. Okay, simply divide by its magnitude. Then we get a unit vector. Okay, now we have some special unit vector along certain directions. Okay, we use ijk to represent the unit vector along the x, y, z directions. So we use special unit vectors. We use the vector I, j, k to represent the unit vectors along the x, y, z axis. The x-axis, y-axis, z-axis, respectively. Okay. So if you have x, y, z coordinate, now the unit vector along the x-axis. So this will be I, and then this will be j, and this will be k. Okay, I, j, k. Okay. So if we have vector, for instance, A is example. If A is I plus 2G minus 3K, we can write in coordinated form, this will be transformed into coordinated form. So this will be X direction, we get 1. Y direction, we get 2. Z direction, we get -3. Okay. B, for instance, B, let's see, for example, 4I plus 7K. Then we add, for instance, how do we add AB? Then we add the component wise 407 component wise. So I correspond to I, so we get a 5I, and then 2G, -3K plus 7K, so we get 4K. Corresponding to the addition of this the coordinate. Okay, 5, 2, 4. Add component wise. Okay. Okay, these are very easy. Vectors are very easy. These properties. Now let's see one direction. Let's see one example. Okay, we can solve physics problem using vectors. Suppose we have a solid wall. And then we have some object here. This is 30 degree, and this is 60 degree. Now suppose we have an object here. We have so we have two strings. The string that has force T1, and then this string has force T2. Now the weight of this object, the weight of object, the given object is 100 pound. 100 pound. 100 pound. So find the tension, the force T1 and T2. Find the force of T1 and T2. Okay, so here this, we have another force which is G, which is we just use 100 pound. So to be more precise, we should use Newton as the unit for force, but here we just use pound. Okay, so if this is in equilibrium, so find T1 and T2. Find T1 and T2. So we use component wise. We use vectors. Okay, this system is in equilibrium. This system is in equilibrium. Suppose this is T1, this is T2. So we should have T1 plus T2 plus G. The total force should be 0. The total force should be 0. This is G. Okay, this is G. This is O. Suppose we have X direction here. This is, we have Y direction. Y direction. Let's use dotted line. Now we use geometry to find the angles. So this is 60. This is 30. So we can write T1 as, we now use direction T1. Now the magnitude of T1. So we find the XY component of T1. So X component is, we can use solving triangle. So the X component of T1 will be T1 times the magnitude of T1 times cosine 60 or sine 30. They are the same. Sine 30, but it's negative direction. Don't forget it's negative. So it's negative this thing along I. So this is X direction. And then plus T1 normal times cosine 30 along the J direction. And then T2 which is we can find T2 times cosine 30, okay, cosine 30. Cosine 30, then this gives us I direction, X direction, plus T2 times sine 30 degree along the Z direction, X, Y direction, okay? Okay, so we get T1 by the equilibrium condition, which should be negative G, which is 100 G, okay? 100 G. G is negative direction, negative Y direction. So negative G should be positive direction. So it's 100 G. So add this together. Then we get add I together, J, add J together, component wise. Then we get component wise. Then we get component wise. We get I direction. You see the addition T1 plus T2. There's no I direction. So the I direction, the I component should be 0. So get a negative T times sine 30 plus T2 cosine 30 should be 0. And the Y direction is T1 cosine 30. Just look at the Y coefficients, the coefficient of G plus T2 sine 30 should be 100. So we have two variables, T1 and T2. We have two equations. Then we can solve this. Okay, this is very easy to solve. So from equation 1, we can get this is very easy. T1 over T2, which is divide. Then you got a cosine 30, which is tangent 60. So root 3, and then you plug in equation 2. Then you get so this we get T1 is root 3 T2. Plug in equation 2. Then T1 is square root 3 T2. Now cosine 30 is root 3 over 2. T2 is just T2. Sine 30 is 1/2. This is 100. So we get so this actually this is the first one is 3 over 2 T2 plus 1/2 T2 is 100. So we get a twice T2 is 100. So that we get a T2 is 50. Okay. Now we get a T1 is 50 times square root 3 T2, which is 50 times root 3. Now the unit is pound. Okay, pound. Okay. So you see, using coordinate, we can project a vector into X direction and Y direction. And once we have equilibrium, we can use physics laws, Newton's law, such that we get an equation. Okay, the net force of this object should be 0. Okay, so that from this thing we can try to solve the tension of these strings. Okay.
Hey, Professor, can you scroll up a bit?
Okay, no problem. If you do engineering, if you have a major in engineering, then this is actually a method that you should know. Okay, this is called force analysis. And that analyze what force an object, what kind of force is on an object, such that you get equilibrium, the total net force to be 0. Such that you get a stable system. Okay, you get a stable system. Okay, any other questions about this example? My picture is so here T1 is T1 should be bigger than T3, T2. So it should be like this. T1 should be bigger, so that it make it equilibrium. Okay, any questions? All right. Now let's now we know how to do addition for vectors. Now you may ask, can we do multiplication between vectors? The answer is yes, we can do multiplication of vectors. Now this is the dot product between vectors. The dot product. So this is the next topic, the dot product. Okay. Okay. Now, given two vectors AB, we want to define the product between them. So, given two vectors, so suppose we have two vectors A and B. A and B. Okay, suppose we have a vector A. Now, suppose we have another vector B with the angle theta between them. Now, we define definition. Then the projection of A onto B. Okay. Then the projection of A onto B is defined as okay. So the contribution of A along the along the B direction. So we just do the perpendicular, find the perpendicular thing. So if you solve geometry, solve triangle, then this part, we use another color. Okay, this part gives us the projection. Okay, this is the projection. So this is the projection onto B. Okay, if you solve by geometry, solve a triangle, you solve the right triangle. This is easy. The magnitude, the hypotenuse is the norm of the vector A. Okay, hypotenuse. But then you multiply the projection over the hypotenuse gives us cosine. So you just the hypotenuse multiply cosine gives us the projection. Okay, the projection. So this is called projection. And we define now the projection is along the is the contribution of A along the B direction. Okay, then we define the dot product, and we define the dot product. We define the dot product between A and B of A and B as a dot product of B as, so this definition, a norm of A dot B times cosine theta. Okay, cosine theta. So this is, if you write in this form, so this you can also write as A cosine theta times norm of B. So this is the projection of A onto B, the projection of A onto B times the norm of B. Okay, times the norm of B. Now this definition is symmetric. If you switch A and B, this does not change. Or you can write as this as if you write this thing, so you get a B norm of B times cosine theta, which is B times cosine theta is a projection of B onto A. The projection of B onto A. Okay, so we get a first property A dot B is equal to B dot A. So it's commutative. Dot product is commutative. Commutative. Okay. Commutative. So it's dot product. Okay. Okay, by using dot product, you see we have three quantity. We have the quantity cosine theta, which gives us angle information. Okay, we also have norm, distance. Okay, length. So this actually is really convenient tool. The dot product is really convenient tool to study geometry problems. Okay. So later we will give examples of how we use dot product to solve geometric problems. Now, we know dot product is commutative. Now, we can also have some distribution law of dot product. So some properties of dot product. So A, for instance, A dot A. Now, the vector A is in the same direction with A. So the angle is 0. So it's actually A normal A, magnitude A times cosine. The theta between them is 0. Cosine theta is 1. So this gives us norm of A squared. Okay, norm of A squared. So we get a norm. Norm of a vector is, if you take square root, norm A dot A. Okay, so we can use dot product to find the norm of a vector. Okay. Now we also know that the dot product is distributive. We have distributive law. Distributive. A dot C distribution. B dot C. We can distribute this dot product. Okay. Okay, this is very easy. This is very easy to show. For instance, suppose it's A. This is, for instance, this is C. This is the B. This is A, this is B. Then we have A plus B. Let's use another color, different color. So this is A plus B. A plus B. Then you see, suppose this is C. Suppose this C direction. You see, this is a projection. Let's use different color. So this part, the green part gives us the projection of A. Use another color. Let's use green, blue, and then the blue part gives us the projection of B. Okay, the projection of B. The blue part gives us the projection of B. Okay, the green part gives us the projection of A onto C. Okay, now A plus B. Let's use another color. Let's use brown. Let's use, for instance, the brown. Let's use red. Let's use red. Okay, you see the red part gives us the projection of A plus B. Okay, so okay, so we are almost done. This is very easy. Very easy. Okay, you see, by definition, A plus B dot C is projection of A plus B onto C dot times the norm of C. You see the projection, the red part is a projection of the addition A plus B. Now, which is, sorry, excuse me. The green part plus the yellow part plus the blue part. The green part plus the blue part. Okay, the green part is the projection of A onto C. plus the projection of C onto, sorry, the projection of B onto C. The blue part, the projection of B, the projection, so this is B, the projection of B onto C times norm of C. Now this is, we are dealing with numbers. For numbers, we can distribute, okay? So this we distribute numbers. Projection of A onto C times norm of C plus projection of B along C times norm of C. And this, by definition, this is A dot C. And this is, by definition, B dot C. Okay, so we should project this law. Okay, distributive law. Now, what happens if we use coordinate? What happens if we use coordinate? Now, if we use coordinate, now the special value, the special unit vectors, what is I dot j? What is g dot k? Now they have a unit norm, okay? The norm is 1 times the angle. What's the angle between I and j? The angle between them is pi over 2, 90 degree, okay? So it's cosine pi over 2 or cosine 90 degree. Cosine pi over 2 gives us 0, okay? So I dot j is 0. Similarly, g dot k, the angle between them is again 90 degree pi over 2. So this we get again, this is also 0. Now k dot I, this is again 0. Okay. Now if we have a vector A, which is x, y, y. Now if you use coordinate x, y, I plus y, j. Now suppose you have another vector b, x2, y2, which is, if you write coordinate wise, x2i plus y2j. Now if you do dot product a dot b, then you get xyi plus y1j dot product with x2i plus y2j. Now, by the distributive property, that by the distributive law, we can distribute. Okay, we can distribute. So now you actually get, now if you distribute the first bracket, let's multiply dot product x 2i plus xyi plus y1j dot product with y2j. Okay, now you do this xi I dot x2i now plus y1j dot x2i. Now remember, I and j, the dot product is 0, gives us 0. So this gives us xyi dot y2j. Now y1j dot y2j. Okay. Now I dot I gives us I norm squared, which is 1. So I dot I is 1. J dot j is, again, dot product with j is 1. So I dot I is 1. So this is x1 times x2, okay, times 1. Now j dot I or I dot j dot product with j, which gives us 0. This gives us 0. Now this gives us, you know, the next term x1 xyi y2j. So I and j, they are orthogonal. Their dot product gives us 0. So this term gives us 0. Now the last term j dot j gives us 1. So this is y1 y2 times 1. Okay. So finally this gives us, okay, so x1 x2 plus y1 y2. So we get the dot product of two vectors. Okay, dot product. I.e., if we have a vector x1, x2, so dot product with, sorry. Okay. Okay, so here did I make a mistake? I switched some notation somehow. Okay, so yeah, xy, x1, yy, x2, y2. So this will be, the dot product will be x1, x2 plus y1 times y2. Okay, if you have three coordinate, then you can do the same thing, but you need a more tedious check. Okay, if you have A, which is a three coordinate, A1, A2, A3. Now you have IJK, use distributive law. B is B1, B2, B3. Now then the dot product between A and B will be now multiplied component wise, okay? And then add the product. So we get A1 times B1 plus A2 times B2 plus A3 times B3, okay? So the dot product in coordinate form. Okay. Example. Okay, once we know dot product, we can find the angle between two vectors. So we know, remember, we have A dot B by definition, norm A times norm B times cosine theta. So we can solve. So this gives us the angle cosine theta. So we can solve theta from the value of cosine theta is A dot B with divided by norm A times norm B, norm of B. Okay. So if we know all the three quantities, A dot B, norm A, norm B, so we can find the angle between them. And the angle is an important quantity in geometry. Okay, to find angles between between two lines. Okay, angles between a line and a plane. Okay, we actually, the main tool to use to do that, a good tool is vector. Okay, use dot product. For instance, example. Let's see one example how we apply dot product to find angles between lines. Okay, suppose we have a unit cube. The unit cube. X, Y, Z. Now suppose we have a unit cube. Okay, we have a unit cube. We have a unit cube, so the thing in the middle, we cannot see them. So it's dotted. Okay, so this is Z direction. So O is 0, 0. So suppose we have A, B, C, D, E, F, G. Now the question, we can find the angle between OG and OA. Find the angle. the angle between OG and OA. Now this is the geometry problem. Find angle between two lines. Well, we can use what we learned today, the dot product. So we can connect the OG. So first of all, we can find the coordinate of G. Okay, we can find coordinate of A. That's easy. A coordinate. Coordinate of A is, X coordinate is 1. Y coordinate is 0. Z coordinate is 0. Now similarly, we can find the G. Coordinate of G is X coordinate is 1, Y coordinate is 1, Z coordinate is 1. Okay, X, Y, Z. You can do the projection. You can find G, coordinate of G is 1, 1, 1. Okay. So we can find the vector OA. Vector O, of course, is 0, 0, 0. X, Y, Z is 0, 0. So OA, we can find OA, which is subject, head subject 2. Now, of course, we can find OG. Head subject 2, then we get this. Easy. Okay, then we can find the dot product. OA dot product with OG. Now it's 1, 0, 0 dot product with 1, 1, 1. So multiply component wise and add. It's 1 times 1 plus 0 times 1 plus 0 times 1, which is 1 plus 0 plus 0. So it's 1. Okay. Now we find the norm of vectors, OG. Norm of OG is 1 squared plus 1 squared by Pythagorean theorem. We get root 3. Now OA is easy. OA is just 1. OA is 1. So then we get, so let C be the angles. Then let C be the angle between OA and OG. Then we have dot product. By definition, dot product. OA dot product OG is OA norm, OG norm times the cosine value of the theta. Cosine value of the angle between OA and OG. Okay. We already know dot product is, this is 1. Okay. We find by coordinate multiplication. Now this OA is 1, OG is root 3. Cosine theta is what we want to find. So, which is root 3 cosine theta. So you can solve cosine theta dividing the coefficients 1 over root 3, which is the, if you rationalize the denominator, then you get a root 3 over 3. So you can solve theta by arc cosine, root 3 over 3. Okay, then you're done. Now we find the angle between the two lines. Okay. More examples. Now, if the theta, if a vector A is perpendicular to B, then the angle between them is, the angle between them is the angle between A and B is pi over 2, 90 degree. Okay, they are perpendicular, so the angle between them is pi over 2. Then we have A dot B will be A norm times B norm times cosine theta, which is, now whatever cosine pi over 2, then we get a 0. Okay, whatever norm AB is, because we know cosine pi over 2 is 0, so we know that actually this is equivalent This is equivalent. Equivalent. If so, A dot B equal to 0. This is equivalent to A is perpendicular to B. Perpendicular to B. Perpendicular to B. Okay, so we have a way to determine whether two vectors are perpendicular or not. Okay, we can determine by taking their inner product or dot product. Okay, we can use dot product to determine whether two vectors are perpendicular or not. Okay, now here, let me give you a little remark. So for vectors, we have the zero vectors. If norm of a vector A is 0, then we have a zero vector. Then we call magnitude A zero vector. Now be careful, zero vector and zero are different thing. Okay, zero vector is different from zero. Okay, zero vector is a vector, zero is a real number. They are different. Okay, so now zero vector has norm 0. Then you have A dot B is 0 if norm A is 0. Okay, i.e. by definition, we know zero vector is perpendicular to any vector. Zero vector is by definition perpendicular to all vectors, to any vectors, to any vector. Okay. Okay, now we determine, we give one example. How do we use vector to determine the geometric condition whether two lines are perpendicular? Okay, let's see one example. Determine, suppose we have three points in space. Triangles. So suppose we have three points in a space with vertices PQR. So suppose we know the coordinate. Now the question is this a right triangle? Okay. Is a right triangle. Right triangle. Okay. To determine a right triangle, we can use Pythagorean theorem. A squared plus B squared equals C squared. And this is equivalent to the right triangle. We can also use perpendicular thing. Okay. For instance, we can check whether two lines are perpendicular. So we need to check, for instance, PQ, whether PQ is perpendicular to QR or PQ perpendicular to PR. Okay, how about RP perpendicular to RQ? Okay, we need to check the three, whether the three. So the first one, if the first condition is true, then we know Q is, the angle Q is 90 degrees. Okay. Then if the second condition is true, then we know P is 90 degrees. The angle P is 90 degrees. Then for the third case, we know R, the angle R is 90 degrees. Okay, we just check. You just check. So we do PQ. Now we find QR, and we find PR. And check whether they orthogonal with each other or not. Okay, PQ. Okay, head minus tail. Q is 2, 0, 4. So you subtract 2 subtract 1, 0 subtract -3, -4 subtract -2. So we get a PQ is 1, 3, -2. And the QR, you just subtract QR. So we let R subtract Q. R subtract Q, we get a, you see, we get a 6 subtract 2, -2 subtract 0, -5 subtract -4. So this we get 4, -2, -1. And a PR. So we subtract the head subtract 2. So it's a 6 subtract 1, -3, -2 subtract -3. -5 subtract -2. So this we get a coordinate 5, 3 minus 2, we get a 1, and this we get a -3. And check whether they perpendicular or not by using dot product. Okay, so we check PQ dot product with QR with component wise 1, 3, -2, dot product with 4, -2, -1. So this gives us component wise multiplication. So you get 1 times 4 plus 3 times -2 plus -2 times -1. This is a 4 minus 6 plus 2, while this is 0. So then we get by the dot product. So we get a dot product. The vector PQ is perpendicular to a QR. So we see, then we know the triangle is indeed a right triangle. So the triangle conclusion is triangle PQR is a right triangle. Right triangle. Moreover, we know the angle Q and angle PQR is pi/2, 90 degree. Okay, 90 degree. So once we know this is 90 degrees, so we don't need to check other thing. We don't need to do more work anymore. Okay. More examples. Find what values of B such that the two vectors are orthogonal. So we have two vectors, -6, 6, and this vector, b squared, and b orthogonal. Orthogonal is another word for perpendicular. Okay, let's use this to be B. Okay, so the two vectors are perpendicular, so we get a -6. We need the two vectors are perpendicular, then we take the dot product. Dot product should be 0. And then we do the dot product. -6 times B plus B times B squared plus 2B, 2 times B is 0. so that we get this should be b cubed plus 4b is 0. Okay, so this we get minus negative 6b plus 2b is negative 4b. So get b times b squared minus 4 is 0. So we solve this equation so that we get b equal to 0 or b equal to plus minus 2. So we have three values. For these three values, 0 plus minus 2, then the two vectors are perpendicular. Orthogonal, okay? Then we're done for this problem. Okay, now we give some geometric application of vectors solving triangles. The law of cosine. The law of cosines, okay? Okay. Now suppose we have vectors, suppose this is C, ABC. We have a triangles ABC. This is C, ABC. Okay, capital word, capital letter, C. Now we use, we often use the opposite of the angle C. We use small letter C, okay? Small letter C. Now the opposite of angle A, we use small letter A. Opposite of angle B, we use small letter B, okay? Now suppose the angle between so that we have, you see, AB. AB is AC plus CB. Okay. AC plus CB. You see, if two vectors head and tail coincide, we can glue them together. Okay. So you see AC, CB, put them together, so we get AB. Okay. Now you see AC. What's the angle between AC and CB? AC is in this direction, AC. Now how about CB? CB is in, so AC is in this direction. CB is in this direction. So the angle between them is actually this one, okay? This is actually pi minus, so this theta, so it's actually pi minus theta. So AC and BC and CB has angle pi minus theta. Now what we do is we take a square, we dot product with itself. AB dot with AB. This side we get AB squared dot product. Use property of dot product. Now this side we substitute AB by AC plus CB. Now dot product with itself. Okay. Now we actually use for convenience. Let's change a little notation. The notation is a little heavy, so suppose this is AC is vector B, CB is vector A, and this is vector B plus vector A. Now if you take dot product, use distribution law, so you get a B dot B plus you have actually cross multiply. You get it twice. You get it twice. You get a B dot B, B dot A, and plus A dot B plus A dot A. Okay, so you get a normal B squared plus twice A dot B plus norm A squared. Now this actually AB is C squared. Now A dot B, this is, so you can write C squared with B squared plus, use definition, twice A times B. the norm, okay, times the cosine value between the angle times cosine pi minus theta plus a dot a norm is a squared. So we have the law of cosine, which says c squared is b squared. If you rearrange the order, usually we write a first, a squared plus b squared subtract. Now cosine use the value, cosine value pi minus theta. The cosine value is negative cosine theta. So the twice subtract 2ab cosine theta. So this is called the law of cosine. The law of cosine. So this is the law of cosine. Okay. Now in particular, if the theta is angle C, okay, angle C. Theta is just angle C. The angle between the line segment A and B. So a particular case, if angle C is pi over 2, 90 degrees, so we have a right triangle, then we get a cosine theta. Cosine theta is just cosine C. Cosine pi over 2 is 0. Then we get C squared, which is A squared plus B squared, which is Pythagorean theorem. Which is the Pythagorean theorem. So we get a Pythagorean theorem as a special case of the law of cosines. Okay. So the law of cosine, you can view it as a general version of the Pythagorean theorem. Okay. The law of cosine is a more general version of a Pythagorean theorem. Pythagorean theorem is a special case of the law of cosine. Okay. So use this example, you can actually determine, from two sides and at one angle, you can determine the length of the other. For instance, if this is this length 1, this length is 2. This is the right triangle. Length is 3, for instance, length 3. Now the angle is 60. Find the angle. This is C, AB. Okay, ABC. Solve this triangle. So AC is 3, BC is 1, angle ACB is 60 degree. Find AB. Okay, we use the law of cosine. Then we got AB squared. AB squared. So this is C squared. This is the opposite of B is B. The opposite of A is A. So you get a C squared is A squared plus B squared minus 2AB times the angle between them times cosine of 60. Okay, so you get a is 1, B is 3. Now minus 2 times 1 times 3 times, remember cosine 60 is sine 30, 1/2. 1 plus 9 minus 3. So it's a 6 plus 1, so it's 7. So you get a C is square root of 7. So we get AB is square root of 7. So we can solve triangles. So it's a more general version of Pythagorean theorem. So we can solve a general triangle if we know two sides and one angle between the two sides. Okay, from the three sides, we can solve the angle theta. Okay, we can solve the angle theta. From the angle theta on one side, we can solve the other side. So we can use this angle and the side to determine all the other quantities. Okay, for instance, how do we determine the angle A? How do we determine the angle A? Angle A, what is angle A? For this example, angle A. Now, by the law of cosine, we see, by the law of cosine, you see, we have A squared is similarly, if you permute the thing around, so you get B squared plus C squared minus 2BC times cosine of A, the angle A. Okay, A squared we already know, A is 1, B is 3, C is root 3, remember. Root 7, we already know. So it's a 2 times 3 times root 7 cosine A. So this is y equal to 9 plus 7 minus 6 root 7 times cosine A. So you can solve 6 times root 7 times cosine A, which is 9 plus 7, 16 minus 1, which is 15. So we get a cosine A, which is 15 over 6 root 7. So it's, if you cancel 3, so it's a 5, 2 root 7, so it's 14. Denominator 14, numerator is 5 times root 7, okay? So you solve A, so you can get A by take arc cosine. 5 root 7 over 14. You can use a calculator to find the angle theta, angle A, okay? Similarly, you can find the angle B. Now we will not solve that, okay? So use the law of cosine, you can determine a triangle. Okay, we have 5 minutes, then let's do inequality. So we know A daughter B is A norm, B norm times cosine value. So we get cosine value. We assume that A, B norm are non-zero. Divide, so we can solve cosine theta, which is A daughter B over norm A times norm B. Now remember cosine theta is bounded. So its norm squared is bounded from above by 1. Bounded from above by 1. So that we can get this thing. This thing is square. This is a number. This square is bounded by 1. Square is bounded by 1. So if you unravel this thing, if you write A as A1, A2, B as B1, B2, then you get A daughter B, which is A1, B1 plus A2, B2. A norm squared will be, so this you get A daughter B squared is bounded by, if you distribute the thing, multiply denominator, norm A squared times norm B squared. Okay, norm A squared will be A squared plus B, A1 squared plus A2 squared. Now norm B squared will be B1 squared plus B2 squared. Okay, now the above is called Cauchy-Schwarz. So we get Cauchy-Schwarz. Cauchy-Schwarz. Schwarz inequality. This is called Cauchy-Schwarz inequality. Okay, so the vector form looks like this: A daughter B squared is bounded by A norm squared times B norm squared. If you write component wise, if you write component wise, this will be this: A1, B1, okay, plus A2, B2 squared is bounded by A1 squared plus A2 squared times B1 squared plus B2 squared. So this is the coordinate form of Cauchy-Schwarz. Now, if you have higher dimension, now if you have 3, now you actually get this. If you have 3 dimensions, then you get the A1, B1 plus A2, B2 plus A3 times B3. It's squared. It's bounded by A1 squared plus A2 squared plus A3 squared times B1 squared plus B2 squared plus B3 squared. Okay, if you have n dimension, this is true in n dimension, then you get, if you use second division, AI BI product I from 1 to n, this squared, this dot product is less than sum of squares of A and then sum of squares of B. Okay, I from 1 to n, I from 1 to n. Okay, so this is the Cauchy-Schwarz, the famous Cauchy-Schwarz. It's a really useful inequality in analysis. You can deduce many other inequalities actually from Cauchy-Schwarz. Okay, although it's really simple, it's derived from cosine theta is bounded by 1. Actually, it's actually really useful, the Cauchy-Schwarz inequality. Okay, we have 1 minute. Maybe we just stop here for today. And let's see if anyone has any questions.
I have a question. So are the homeworks and are going to be on WebAssign or Canvas, or how are they going to work?
I will post the homework problems.